Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Steve McDaniel, who's flown in from Austin today, where his company is located. That's Reactive Services, which you're going to hear a little bit about today. Steve did a BS in biology at the University of Texas, and he did a master's in genetics at Texas AMU, and also did a PhD in biochemistry at Texas AMU. He then did his postdoc at Baylor College of Medicine, and then his career darted off in another direction. He did a law degree at University of Houston, and since then he has concentrated in the area of IP litigation, and he's now a member of the Bar of the Supreme Court. He has trials experience in Federal Southern District of New York.
I told you he was going to speak poorly of me.
East District of Pennsylvania, and all districts around Texas. And then, obviously not content with that as a career, he's also, in 2002, formed his company Reactive Surfaces, which is a bioengineering company. They use molecular biology for functional additives to coatings and surfaces and paints, and we're probably going to hear a lot about that today in his talk. And in addition, I met Steve through the Mars Society, but he is now part of the Explore Mars group, which he might tell us about in the talk, or you might want to ask him afterwards in the question time as well. So if you'll join me in welcoming Steve.
Thanks, Adrian. I didn't know you guys were going to serve my very favorite food, peanut butter and jelly, or I had to come earlier. I have to make a disclaimer to you, being a lawyer, okay? And that is that I am, so let's see if this is working. I guess this one isn't working. Let me try this one. And that is that these people right here are real space scientists. And you see this guy over here? He is not a real space scientist, okay? And I can prove that definitively to you, okay? While it is true that I've done a lot of space advocacy through the Explore Mars group, through the Mars Society. In fact, I first met Jennifer on the very first crew to go into the Mars Desert Research Station. We call ourselves the Alpha Crew for whatever reason, and I have done that. I am not trained in anything remotely similar to space science. As Adrian told you, I'm a molecular biologist by training. I happen to get a law degree, but that's really sort of ancillary to what I do. And so I do on occasion, however, I do speak to groups. My kids are 5 and 7. I do speak to their classes in high schools about space and these kinds of things. And on one occasion, I was talking to a group of kindergartners, and they were all around a table. I had my Mars globe there, I had my Venus globe there, I had my Luna globe there, I had an Earth globe there. And I posed the question, does anybody know what the largest planet in the solar system is? Well, absolutely, all 14 hands shot up. They're all waving their hands. And there was this little girl that's just waving her hand feverishly. So I called upon her, and she still had her hand up. And she said, I don't know. And I said, that's okay. That's cool. That's all right. And I said, does anybody else? And she's still waving her hand feverishly. And she says, but. And I said, but what? And she said, I like salmon. And I said, that's very good. I do too. I like salmon. And she goes, and I go, and what? I was getting a little kind of annoyed. And what? She goes, salmon is brain food. So I'll bet I can figure it out. And I thought, whoa. That's a really good answer. So I said, if I told you it started, and before I got the letter J out of my mouth, she said Jupiter. I said, you know what? I'll bet you like salmon. So here in a minute, when you ask me questions about science, space science in particular, and I say I like salmon, you'll understand what I mean. I don't really probably know the answer to your question, but I do like to ask questions, and I do like to answer them. And so we will talk about my company. We're going to be talking about not so much what my company is and what we do, but rather to, I hope, give all of you an idea that there are materials, there are solutions to questions that you might not have even asked, and there might be solutions to some problems that you have with optics, with devices in which you have to operate through a touch screen, places where you have to make absolutely sure there is no biofilm around, places where you have coatings, places where you have sensitive equipment, places where you're going to stick humans and ask them to live for a very long time. Maybe there are some materials that you don't know about. So I hope I can imbue you with that today. You know, coatings, and my company is about coatings, just like Adrian said. Coatings are absolutely everywhere. There is almost virtually nothing that you have that is man-made that doesn't have a coating on it. And that includes everything in your personal space. Anytime you're around man-made objects, they are coated in some point in their manufacturing process. There are, they can be measured. For instance, if you take the cell phone, or a cell phone, if you've got a cell phone in your pocket, your computer or whatever, you can measure the length and the width of them. And if you calculated all the area around here that's coated, it's an enormous amount of area that's in your personal space. Anytime you're there, your clothing, your glasses, whatever, those things are coated. It's an enormous area for you to play in, all right? As I note here, I mean, you can literally, there's really nothing that you can think of that isn't coated that's not natural. So you take, for instance, this right here, which is a two-part polyurethane coating that my lab team at Southern Mississippi did for me. This is a polypropylene block right here, and they painted this. This is exactly like the coating would be on your computer. And to your touch, it's a very smooth coating like this latex on this wall right here. And we can measure that length and width, and we get a certain surface area, okay? But the surface area that truly possesses is anything but merely obtained with the calculation of its length and width. Because if you drill down at that and you look at an 800x close-up, this is a coating that feels smooth to your touch. Okay, just as smooth as the chair backing. It's very smooth. And yet, look at all the nooks and crannies and hills. Look at all the pores. Look at all the places for things to hide. Okay, that's an 800x view. What if I take this very same coating and turn it on its side and that polypropylene block and slice down through the middle of it and train my scanning electron microscope at the side of it? Well, that's what it looks like. Here's the polypropylene block. This is a 20 micron bar, and here is the actual coating itself. This is coatings. People think of these things as massive areas in which to play. That's a pigment particle. That big blob in the middle, those are pigment particles. These are titanium dioxide crystals that give this same coating kind of a whitish, gives it just a whitening agent. And there are pores all the way down in this coating, all the way down to the subsurface on which it's painted. So the actual surface area underneath your thumb on any coating that you place it on is absolutely huge. Now, coated surfaces historically have done two things. They have protected the underlying surface on which they're coated, and they have, in many cases, decorated that same coating. Some cases it's a clear coat, and like this coating on this flooring right here, the coating that goes on here is clear, and so you can see the underlying pigment in the carpet. But on average, they either protect and decorate. But what if you could take this immense amount of surface area and you could make it do something dynamic in your personal space? What if you could have something happen with that coating every time you walked into a space or every time you put a clothing on? What if those coatings actually interacted with you in your environment? Okay? Well, that kind of a coating would be called a reactive surface. And there's why we named our company Reactive Surfaces. Okay? I'm going to be talking to you today about those very kinds of surfaces. What we do in order to take those surfaces and make them functional and make them do something dynamic in the spaces in which you are interacting with those coatings is to take basically biological molecules that we do. Again, I'm a biologist. Take biological molecules and stick them in this matrix called paints and coatings and ask them to do whatever they were doing in nature in the coating. All right? So it is our slogan, bringing coatings to life, but it's actually what we do. And I'm going to show you how we do that. What we do is we take historically the gears of material science. I'm talking about polymer sciences, making laminates and making coatings and making paint and building materials and paper and all those kinds of things, has spun rather independently of the gigantic gear over here in space called biotechnology. Okay, they basically have spun independently. What we are trying to do is to actually become the mesh between those two gears so that we actually create, using biotechnology, and materials that are new and functional. This is how it works, and we're going to talk about each one of these today. We take the two industrial sciences, we innovate out of them, and you're going to see, for instance, that we have molecules right now today that can decontaminate toxins off surfaces, that can keep surfaces microbe-free safely, that can actually remove the fingerprints off of surfaces on your touch screens and on your telephones. You'll see these kinds of things in action today. On the horizon, however, and when I say on the horizon, what I mean is they are past the proof of principle, patents have been filed on them, these things are actually in the labs right now, are surfaces that will, for instance, be useful in defouling marine anti-fouling coatings, defouling, keeping microorganisms and biofilms and barnacles and the like off of marine coatings. Molecules that actually self-repair coatings, coatings that are been damaged by radiation, so such on the exterior of a craft of some sort, that made out of composites that actually self-repair themselves. Coatings that can be actually renewed, that is, that they will uptake components that you introduce to them and absolutely, and actually become functionalized yet again, sometimes in some cases actually reprogrammed. We have antimicrobial enzymes that give us very nice antimicrobial surfaces. And the really cool one, and this is the one that's going to be really fun, and we're starting to see this, is when we can actually take functionalities that speak to one another, where they are actually, this molecule is creating another a product, this molecule is taking that product up and converting it to something else. Now this is all taking place in your coating, okay? So that's what we're going to talk about. People always ask me this question, so I'll tell you how it is. It sounds like, maybe it sounds like we've got this gigantic organization. We don't. Little bitty RSL is the hub, but it is a fully outsourced model. At the center of it is my law firm, the technology law firm. We have labs that are right there next to our law firm offices. Some of our lawyers are PhD molecular biologists as well, and they work with the lab people all the time. We outsource to a variety of different universities. We do all our polymer sciences at Southern Mississippi, Texas A&M. We do a lot of biotechnology and genetic engineering. The University of Georgia, we do a lot of the manufacturing, scale-up manufacturing. And then we have some admin people who are, we're a startup, so we have to have capital investments. And we do some marketing through another firm. So those are those people. Those people actually are real people. They're all board members and in many cases owners of the company. So it's a very tight glue. All of these different people here, I'm giving credit to the people by this slide that have done a lot of the work. So let's take an example so you really kind of get an idea of what I'm talking about. This particular product is called Degrees. What do you think it does? Yeah, I wouldn't be able to guess either, sorry. But here is this molecule working, and I have to spin this by touching this. These are two coupons, one of which on the left is a control, one on the right is the one that has the additive in it, and these are crapped out with your kitchen's worst nightmare of soy oil, and you can see, and I'll spin it again for you, I'll move the hand out of the way, you can see that the control panel remains greasy, while this panel, without anything further, doing it on its own, self-degreases itself. Let me spin that in for you again. So when you walk up some vegetables like this young man's doing, and you have laminated countertops that have degrees in them, and you go to bed because you didn't feel like cleaning up that night, you come back the next day and all the soil oil, vegetable oil on your surfaces has actually been self-cleaned.
What is the time period?
This particular frame, I think the time power it was 12 hours.
12 hours
after we put all the grease on top of it. We did that for demonstrative purposes. Well, let's hope that you don't have that kind of a kitchen disaster, all right? Okay, yes, sir.
So it hydrolyzes it.
Yes.
And so it turns into
Glycerol and fatty acids.
fatty acids.
That's right.
Those in turn are easier to clean up?
Those are water soluble. You can clean them if you wish. You don't have to clean it in order. I mean, the oiliness is gone. Okay, and those products are in fact water soluble. So instead of cleaning up this, well, good luck cleaning this coupon, right? Without a lot of soap and water and elbow grease. This one right here, you can clean with a damp sponge. Okay.
It retains the water for hydrolysis from the environment?
It's surprising. It's a great question. The question is, the hydrolysis, meaning the adding of a molecule of water across a bond that breaks the grease and into its component parts, that is glycerol and fatty acids. Where does that water come from? And the answer is it is environmental. As we began doing this research, we found out that most coatings are hydrated more than you believe, even in very dry environments. In many cases, it's as much as 90% capacity in hydrated and coatings, especially inside buildings where there's a lot of humidity, clothing and the like. The humidity is plenty enough to drive. We're talking about molecular water, right? We're not sloshing around water, right? But we're talking about molecular water, plenty of molecular water to drive the reactions forward.
Well, in connection with that question, are you going to tell us reveal the structure?
Well, I didn't know what level to gear this at, but we can certainly do that if you wish.
This is not the secret.
No. What's the secret of this? Yeah, I'm going to show you that.
Are the molecular structures secret or?
No, not at all. This additive, this particular additive is something called lipase. It's a well-known enzyme. If you've ever bought enzyme activated Tide, it has lipase in it, cellulases and things like that.
How is this different from self-cleaning ovens?
How's it different?
It operates at
Well,
room
actually,
temperature?
it operates at room temperature. Enzymes are very good. Take your body, for instance, that drives on enzymes, are very good at carrying out reactions that would require a very large thermal influx or heat or energy influx if it weren't for the fact that they are rigidly holding certain molecules in space such that they can actually reduce that energy requirement.
The activation energy.
That's correct, the activation energy. Right, exactly. Great questions. All right, so let's move forward and look at another one of these things. Here is an example of us actually taking the lipase enzyme, placing it into a laminated material like you'd find on your kitchen countertops, and producing the very first self-cleaning countertops. These materials will be available within the next year to a year and a half. You will be able to place in your kitchens laminated materials, countertops, and the like, in any place you have a laminate, they will self-degrease themselves. OP-detox is another example of an enzyme that we utilize in order to functionalize a surface. Now, some of the things that I'm showing you will have very little relevance, at least at first blush, with spacecraft and, for that matter, any kind of space equipment. This one in particular was designed as a military product. This particular molecule will actually decontaminate organophosphorus nerve weapons from the surfaces of coated surfaces. This is one of the very first ones we did. My PhD was actually on this enzyme, so that's the one that we worked with. I'm going to run this again, but let me tell you what this experiment is. Basically, you have an acrylic latex painted on a big coupon, a metal coupon, just like that tank had that M1 Bradley has on it. And then we have on this side has no additive in it. On this side has the OP-detox additive. Then we trap under Petri dish tops 100 fruit flies on each side after we've actually contaminated this surface with a simulant of a nerve weapon called peroxin. So I'm going to spin this again for you in a minute. Watch the flies on the right, in which there is no additive, and the ones on the left, in which there is an additive. And as you can see, the ones on the right, no pun intended, die like flies. The ones on the left remain happy and healthy. And that works the same way for the soldier sailor as it does for those fruit flies on those surfaces. We've done testing with NATO, and we're testing right now with the Army Research Laboratory to show that this works the very same way with the nasty ones like VX, sarin, sarin and tobin, and soman. And it works nicely. It's very useful for military vehicles, also for our textiles, and it is in particular useful in instances in which there are low levels of neurotoxins that you do not detect necessarily, but in fact do light on surfaces, by the way. You hear the term nerve gas sometimes. These things are not anything close to a gas. They are actually they are aerosolized droplets, and they light upon surfaces. That's what they're designed to do. So that when you touch them, a 70-kilogram man touches a surface that has VX on it, enough VX to coat the end of my little finger will kill me in about 10 minutes. And so it's a contact problem. It's a contact surface problem. We've got to get those toxins off there. Now, what I said was that particularly does not have very much relevance to you in the spacecraft, obviously, but there are a lot of things, environmental toxins, that we do want to handle inside of spacecraft, or for that matter, any closed environment in which we are aerosolizing, cleaners, these kinds of things. This is an analog, OPD tox, for instance, is an analog of ridding, using surfaces, all these surfaces, say if in a spacecraft or in this room, of things like pyrogens and allergens, those kinds of things that would be susceptible to functional coatings. We can do it by enzymatic clearance. That's the way we did it with OPD tox. We can also sequester those nasty molecules using things like receptors and antibodies, because we have proven that you can entrain a biological molecule into a coating and expect that biological molecule to do exactly what it did in nature in the coating, and to do it for a long period of time, repeatedly over and over and over again. Okay? Now this one, though, has a lot of relevance to the space environment, because this one is not an enzyme, but rather a peptide, and this one solves the age-old problem that Lucy posed to Linus. And that is, Lucy says, "Why are you always so dirty?" And Linus rhetorically answers basically, "Who am I to disturb the dust of countless ages?" Okay? The truth of the matter, folks, is that we are all pigpens. Well, I am it. Okay? And when we take this guy and we place him in a closed-loop environment that has toilet facilities, bathing facilities, myriad surfaces everywhere, and we eventually get to where we actually cook and do other things like that in this environment, we will take with us this microbial load despite our best efforts. Despite our best efforts. The stories are legion of the myriad. We just finished the cislunar workshop in Galveston last year, and there's still talk about the black mold behind the towel racks on ISS. I mean, it's a situation that we have to deal with, especially with long duration spaceflight. Now, we do not have the liberty, obviously. We do not have the liberty of airing that thing out. Okay? We do not have the liberty of spraying a bunch of Lysol on all the surfaces. We've got to do something that actually lets us live in this environment in a synergistic way with these very same microorganisms. Now here's an interesting point, interesting fact, at least it is for me. The National Institutes of Health have launched a program called the Human Microbiome Project. And what it is basically like the Human Genome Project, except what they've undertaken is to actually identify all the species of microbes living on the average human body, to genetically analyze them, see the numbers of species, the concentrations where they live on the body, and to actually identify them. Believe it or not, we haven't even identified all of the microbes that live on the average human body. We don't know what they all are. That's weird to me, but that's true. Now, here's the fact. Your bodies are comprised of about 10 to the 14th human cells. If you counted every single cell in your body, you have about 10 to the 14th human cells. Your bodies are populated by anywhere from 10 to the 16th to 10 to the 18th microbes. You are, for all intents and purposes, on a per capita basis, more a microbe than you are a human. And that's the truth. Now, that same plethora of microorganisms are absolutely required for your existence. If you disrupt that microbiome, you will be sick. If one of those microorganisms takes off and grows too large in the population, you will be sick. If it's not big enough in that population, you will be sick. You depend on them just as much as they depend on you. And so when we say we are going to space, we have space travelers that are going to go with us, and they must go with us. Okay? They do exactly what you see happening with Pigpen. They leap off our bodies, and they get behind the towel rack. Okay? And they get down in the toilet, and they get in the ecosystem, they get in the air ducts, and they grow. So, how is it that your body handles this plethora of microorganisms on it? Why don't they just, because, by the way, these are the same microorganisms that when you quit breathing will do a really, really good job of turning you into a blob of jello. Okay? Really good job. Fast. Really good. Okay? How is it that we keep our bodies keep, not just our bodies, but plants, all sorts of animals to do this. How is it that we keep this plethora of microorganisms in check? Well, one of the ways that we do it is that we produce on our surfaces of our bodies something called antimicrobial peptides. And these don't necessarily, remember, we can't kill the microorganisms necessarily, but we certainly have to control their growth and keep it in check. And antimicrobial peptides is one of the ways that we do it. So here's an example. This is not a spacecraft, obviously, but a fence. Paint guys like to paint fences. One of the things that just drives me crazy is they always got to, if you give them a new paint, they got to go slap it on a cedar plank and stick it outside and let it go for 3 years. That's just what they do. They paint fences. So here's an example of a fence at the University of Southern Mississippi where we have some of our teams with a coating that has the protocote molecule in it. It's a peptide that kills microorganisms. Wasn't in the control coating, was in our exterior paint coating, and though it's not easy to tell like this, but there is a dinginess and a grayness to this control paint that is missing from this particular paint where it has the additive in it. And what you'll see is that dinginess is actually caused by a jillion, basically these are fungi and algal colonies. You can't see the bacterial colonies, they're not large enough. But you can see that there are a lot. The crazing that you see is actually normal paint film stuff. That happens with all paints. But those dots are actually a lot of microorganisms growing on that paint. If you look at the same magnification on this paint, you can see that there are virtually no microorganisms growing on it. This is after 48 months outside of the exterior, outside of Southern Mississippi. Now, I have to remind you of something. You could get that same effect if you put a bunch of lead in that paint, or a bunch of tributyl tin, or a carbamate, or some other really, really nasty thing, okay? All this has in it, ladies and gentlemen, is a very short little peptide, 7 amino acids long, that you can literally put on your Cheerios and get a protein boost from. You can eat it, all right? But it is hell on wheels against microorganisms. Yes, sir? I am, but to answer your question in a short way is because industry is absolutely reluctant to have to change anything in their process. You have to make it act exactly like all the additives that they pour into these coatings every single day. And basically it has to be either a powder or a liquid that you just pour in, and you're going to see me do that in just a minute. But it's called a drop-in. It has to be something that's a drop-in. It fits the already existing industrial manufacturing process. All right. It's a great question because you ask yourself, well, gosh, these things are derived from nature. I mean, they're enzymes. You have to refrigerate them. I mean, what do you got to do to them? The way we've done it is to take the down and dirty approach, and that is to say, no, these things just basically have to be a powder that you can store on the shelf. I'll show you in just a second. All right, so this is all fine and good. You can see it controlling microorganisms on the exterior of on the outside surfaces that you might encounter on the side of your house or whatever. Here's an example of what we did for the Boeing Company. The Boeing Company has a problem that I didn't realize, and that is that, maybe you all know this, but Boeing primarily leases aircraft. They don't sell aircraft, they lease aircraft, okay? And therefore they are in the line of fire if contagion ever leaps across the ocean on their aircraft. At least they believe they are, okay? And therefore they are very concerned with aircraft that the pig pens, walk into and walk out of, and walk into and walk out of, use the tray tables, and they never get cleaned. And the lady behind you is sneezing her head off, and the guy in the front of you is coughing his head off, and they go through a big air conditioning system that doesn't have a filter on it. It just basically recycles the sputum and off of the cough and right back into your face. They have a large concern. Sorry to, by the way, they do have a filter. They have a HEPA filter down in the cargo hold. It's freestanding. If a molecule of air happens to go through it, it gets filtered. They are required to have a filter. Okay, that's how it works. Yeah, a guy from Boeing told me that one day. I'm like, dude, I wish you hadn't told me that. You know? So they were very concerned, particularly about their tray tables. That is, they've done the test. They know how nasty those things are. All right, and so what they ask us to do is we want you to compare our standard biocides, quaternary silanes, nano silver, to your protocope molecule against a bacteria on coupons, painted on coupons, and ask whether it does immediate killing, which does the best job of immediate killing in 75 minutes, and which does the best job in 8 hours. And here's the results. This is, by the way, a logarithmic scale over here that shows the killing. Actually, this is the reduction in colony-forming units. Microbiologists talk like that. But anyway, the log reduction in killing. This is the this is the quaternary silane. This is the quaternary silane plus nano silver together. This is the silver by itself, and this is protocote. This is the peptide, okay? And this is a log scale, okay? The differences don't get that much better even over time if you go to 8 hours. The peptide still beats the standard. These are the fair-haired children of the antimicrobial world. Nano silver's got a big following right now, okay? Here's an example that we did for another company out of Mexico. They were particularly concerned about clinics, schools, and the like, and they actually isolated some clinical strains that they were very problematic for them, and they asked us to look, again, at a logarithmic scale, whether protocote, shown here in the green, did a good job of knocking down these various strains. This one in particular, Staph aureus, this one was you've heard of the term MRSA. You know, it's a multiple resistant Staph aureus. This was a multiple resistant Staph aureus. And you can see protocote again doing a very good job against clinical isolates. Now, I pose to you that that surfaces on the ISS and the deep space hab that we're going to be building, we hope, that those surfaces should have in them, and by surfaces I mean all the surfaces, should have in them at least something like a protocope molecule or enzymatic way to actually reduce the amount of contamination on the surfaces that we will come into contact with again and again and again and again. Okay? And it has to do so safely and long term. It's also very good at actually controlling algae. This is the control. You can see the rings of inhibition around painted surfaces that have protocote on them. This is in particular of interest to some folks in Europe who build what they call structural mortar. We call that stucco. There's a lot of stucco used in Europe, and that gets a lot of cyanobacteria on it, and you get green slimy walls. Now here's an interesting one. This is very preliminary, folks. Don't bank this just yet. But we're fairly certain that that protocote does a good job against what we call encapsulated viruses. These are the nasty ones. This is Ebola, HIV, the ones that have certain environmental persistence, because those very viruses have have an envelope around them that is susceptible to the protocoat mechanism. So cross your fingers, but there may be a way that we can actually have antiviral surfaces. Again, just to emphasize one more time, that these molecules are absolutely non-toxic. Category 4 is the EPA's way of saying that on the label that you are going to put on your paint, you have to have absolutely no cautionary statement. There will be no cautionary statement required by these, okay? Because they're completely non-toxic. Now here's another one. We talked about peptides. This is one we call Renew. And we call it Renew because we can continually modify this surface in a way to make it do what it did at the beginning again and again and again. This one came about when we started thinking about the problem with anti-fouling surfaces. Anti-fouling surfaces are traditionally made out of heavy metals. San Francisco Bay has got a bunch of copper in it. You probably are aware of that. And we've been using these things since the time of the pharaohs and the Vikings. We've been using metal on the bottom of boats and silver as antimicrobial, and Egyptian physicians were using it. But these coatings that are made out of this heavy metal, let me see here. Oh, well. That are made out of the heavy metals are very, very poor coatings. They give you very, very poor fuel efficiency on the bottom of the boats because they're bumpy and they flake off badly. And they're being banned around the world. My understanding is the state of California is presently considering legislation that will not only, they already have legislation that says you can't paint your boats with heavy metals, but they will have legislation pretty soon that you may not bring your boat into a California bay if it has a heavy metal on its bottom. We can't paint it in Singapore and bring it here, okay? So what they've done, what the shipping industry have done, is gone to coatings that are basically, we call them Teflon coatings. They're based on fluoropolymers that as there is hydrodynamic pressure of the vessel moving through the water, because it's really slick, they actually knocks off the fouling off the surfaces. But for those to work, they must be underway. They must move. If you do not have that hydrodynamic pressure, it will not remove that fouling, okay? Well, it turns out, folks, that nature abounds with protein and peptides, and we call them domains. These are just sections, if you will, of peptides and proteins that selectively bind and release heavy metal. That's how they work. Many, many proteins in your body have at their core a zinc, or a copper, or a nickel, a divalent cation, or more than one. It also turns out, of course, that seawater has significantly dissolved heavy metals in it. And I'm not talking about the ones in San Francisco Bay because people have been using copper bottom boats. I'm talking about just average seawater. Has a lot of heavy metals in it. What if it were possible to entrain a metal binding peptide into a slick coating and actually get on the bottom of the boat a peptide that removed the metal it needed to be antimicrobial from the seawater itself, and then selectively release this metal so that it could actually control fouled organisms on boats? Well, it turns out that it is possible to do so. So we have entrained metal binding peptides in hydrodynamic coatings, placed them on metal looking like ship hull metal, and ask a solution, we have used simulants of seawater, ask a solution with heavy metals dilutely dissolved in them to be sequestered in this surface, and for that surface to actually express an antimicrobial capability. And it does a very good job. And so we will be able to, this one is a little bit further back in the drawing boards than some of the other ones I just talked about. But we will be able to, we hope, to provide shipbuilders with a new coating in which they will not have to use heavy metal, but they can rely on the very, very good antimicrobial capabilities of these metals. Here's an example of it actually working. You can also see that it works with different metals, some worse in the case of cobalt, some better in the case of nickel. And you can actually reprogram these. Sometimes you could use copper as the charging metal, sometimes you could use nickel as the charging metal, and it can be switched. And you do that without having to repaint it. Now the question is, how does that apply to the spacecraft scenario? Well, you don't have to use seawater. You can actually utilize just spun-on dilute solutions, okay, of copper sulfate or silver or whatever. so that you actually produce, we would hope, a non-toxic antimicrobial coating in spacecraft. We won't have to aerosolize Lysol and everything like that. We can just wipe down these surfaces with metal binding metals, heavy metals, so that they create an antimicrobial coating. Caduceus is one I'm not going to spend very much time on. In fact, I think I'm going to skip it because I want to have time for everybody to ask questions. Is the self-repairing molecule that I talked to you about. Composites. Let me give you this one factoid. You know how we're building these very, 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 very large blades on wind power generators? Well, those are built with composites. Those are polymers that are built on composites. A balsa wood core with a very, very thin film of a composite material on it. Those things are actually failing in some cases in 9 months once they've been installed. And the reason they're failing is because the thin veneer of the polymer is actually being irradiated by sunlight. It's also being torqued. And at the molecular level, those ester linkages are being broken. And it's a cataclysmic failure. Once it reaches a certain critical mass of strength. Composites are strong because they're molecularly strong, not because they're patched up like fiberglass. They're molecularly strong. And once that strength gets to a certain critical mass or reduces to a certain critical mass, these things come apart at high speed. And they cost about $1 million a blade. Okay? So this is a molecule that does that. You asked the question, someone, what do these things look like? I'm going to skip this slide. We just pour, there's degrease going into a reactor when we were building laminates, self-degreasing laminates, countertops, just to pour in. This is what OP detox looks. It's just a powder. Protocoat is just a powder off the shelf, for special treatment or things like this. Now, I put this up there because I think it's important for you to get an idea of the size, okay? Remember at the very first of the talk, I told you that I cut down through a coating. This is about 20 micron coating. And those are all pigment particles and titanium dioxide crystals. Those things are about 500 cubic centimeters. These things are about 50 cubic centimeters. A bacterial cell itself is only 0.6 to 0.7 cubic centimeters. We can't even, it's not even rational. Huh? What did I say? I'm sorry. Wow, that'd be a big bacterium. Don't want to meet that guy. Okay, micrometers, my apologies. But at any rate, it figures you guys can do it. I mean, you're always measuring things in nanometers and all that. Yeah, okay. All right. So, but it's not even rational to talk about cubic micrometers in the terms of an enzyme. These things are only measured like, this one is the 31.7 kilodaltons, and this little peptide over here is only 7 amino acids. It's less than a kilodalton. I mean, it's little bitty tiny things. Now, if I can pack 500 cubic micrometer particles like these pigment particles in this coating, think how much of these things I can pack in this same coating, okay? A lot, okay, when you functionalize surfaces. All right, so arguments in favor of functionalized spacecraft coatings. The additives are easily made and integrated into any coating in the spacecraft. Because the functionality is derived from the coating itself, there is no, the load on the ecosystems should be substantially less. That is actually a net weight reduction. They don't weigh anything themselves when they are added to the coating, so that's nets itself out. Because you add them prophylactically and because it remains dynamically active throughout the mission, there's a significant reduction in the need for pre-launch preparations, such as sterilization. Of course, the last satellite I think we actually sterilized was a Viking. But anyway, the molecular compositions of the additives is nothing more than protein. So it's leaching from the surfaces, if it does in fact do so. Poses no greater concern than the presence of the humans in the craft itself. We're constantly shedding keratin and proteins and lipids all over the place, okay? And because the crew maintenance of self-sterilizing and self-cleaning and self-repairing coat is significantly reduced, it has an overall increase in crew efficiency. At least those are my arguments as a non-space scientist, okay? Our approach, we think, is, I'm going to skip over this, actually. We do a lot of innovation protection. We do a lot of publications. We won the American Coatings Award in 2008 for some of this work. We do a lot of work with companies that are eager to, when the products come to fruition, to actually take up those products. For instance, one of the ones that I just told you, Wilson Art is going to be the group that's coming out with the self-degreasing countertops. And we would love to work with NASA on coatings for spacecraft and for rovers. That's something that we're going to be actually presenting a business plan to NASA here pretty quickly over. And it is a very sustainable model. Nature abounds with functionality, and if we can shove our little machine right up next to it, we anticipate a substantial amount of innovation in the area of material science and coatings in the very near future. So, thank you very much. I'm going to go get my PB&J sandwich.
Steve, if I could kick off the questions with, as you mentioned, we carry around a lot of microbes ourselves. What if we're putting something on the surface that's killing a microbe that we need, and that we, suddenly lose from our hand because we?
It's a great question, and what we have to do, obviously, is we have to maintain a balance. We don't want the black mold growing on behind the towel rack in the crew bathing area. Okay. On the other hand, we do not want to touch a surface that would somehow eradicate a useful yeast that's on our skin. Okay. But it really is a mass balance question, isn't it? In other words, obviously, my touching the surface, I touch nasty surfaces all the time. Okay. As long as the molecules are entrained in the coating, and that's what they are, okay, they will do what they do functionally in that coating. Once they leave that coating, they're nothing more than just the proteins that you are normally leaving out there anyway, and they are very rapidly degraded by the existing microorganisms. Very, very, very rapidly degraded. Yes, sir? Yes?
Oh, I'll just go. So enzymatic activity is strongly determined by things like pH and temperature and solution.
Mm-hmm.
How do you prevent these biomolecules from denaturing when you go from a liquid phase to a solid phase?
That's an excellent question. Actually, as you probably are aware, in the sol gel state within a normal cell, they're just packed solid with solids. In other words, the interior of a cell, you may think of them as water bags, but really they are high solids suspensions. Okay, so enzymes like to be nestled in and tightly packed with each other, and other things like lipids in the membrane, lipids and polysaccharides and things like that. They like to be down in that. And what we have found, to be honest with you, somewhat surprisingly, at first I didn't think it was going to work. I really didn't think. They told me, I'll tell you, right after 9/11, this company came into being. And the reason it came into being is because an investigative reporter was going all around the country trying to find out what we're going to do about chemical weapons. Everybody was really worried about chemical weapons. We still should be. But they're really worried about it. So a TV team came in my law office and interviewed me about what I had done as a PhD, and that is to work with enzymes that decontaminate organophosphorus nerve weapons. And they asked me the question. They said, why don't we just build this stuff and use it? I said, well, because it does. It's a mass balance problem again. I've got this stuff floating around in the air. And there's lots of things I can decontaminate it with, but to get it in contact with that thing is the problem, isn't it? Okay? If I could put these things in surfaces, and if they would actually survive in that surface, then I shift that mass balance problem to my favor, okay? That enzyme's in that surface, here comes the nerve weapon, it settles on that surface, and I gotta attack it. So to answer your question, when they said, is that possible? I said no. For the very reason that you're saying. It is going to come apart, denature, or the pH is going to be wrong, or there won't be enough. Someone asked the question about water hydration. There's not going to be enough water around to drive the reaction, or whatever. But what we have found is that enzymes really, really, really like coatings. And we think it's because it constrains them. There's a lot of, enzymes are dynamic molecules. They're constantly moving. They're constantly moving. But if they are in solution, if they're out in water or something like that, they're moving so fast that they eventually kind of open up and denature. But if you can constrain them and you keep them very tightly constrained, they have enough movement that they can do their job, but they don't come apart. That's the kitchen biochemistry answer to your question.
So you're saying
yeah.
by nature, when they go from liquid to solid phase, they don't lose their functionality. There's nothing that you actually do to them.
Well, I can only say that for sure, that they work in coatings and they maintain their structure for long periods of time and continue to do the function that we placed in the coating for. Now, it may be, it's going to be very interesting to actually answer your question on a thermodynamic basis, right? That's going to be a very interesting question to answer. What are the actual thermodynamics here? I mean, how is this thing actually moving, and why aren't they coming apart, and why is it that they're okay being entrained in this matrix, this coating matrix? Okay, the biochemistry gets really weird though, because normally we do enzymatic thermodynamics and enzymology in solution, and doing it in a solid is a totally different thermodynamic question, and we just haven't had time. It's worked out of the chute. We haven't really run into one yet that we can't. We will. Okay, we will. But we will. And especially when we're not talking about hydrolases and things that are just naturally very hardy. Okay, we will run into problems.
I have just a general question. How aggressively are hospitals pursuing these antimicrobial coatings? Like I hear they use copper, they have copper
Silver.
counters and that type of thing.
Yeah.
They should be looking into this, I would think. There's all kinds of bugs there.
Well, trust me, we're pushing it. Okay, but there's a problem that hospitals have, and it's because of lawyers. Hate the bastards. and it's because once you say you have a problem, then you do have a problem. Okay, if I say that I've got nosocomial infection rates, they don't use that anymore, but hospital-acquired infection rates that are in excess of 10% of my patient load, I got a problem. Okay, why is that? Well, my surfaces are contaminated. Well, you're going to have to close your hospital. As a matter of fact, the new Patient Care Act says, I think in 2016, if it survives the Supreme Court challenge, is that the hospitals whose nosocomial infection rates are in the bottom 10% of hospitals nationwide will be fined substantially, and those same fines will be then used to reward the hospitals that are at the top 10%. Okay, Walter Reed, portions of Walter Reed just got shut down. I mean, about 3 years ago, got shut down because they could not control the fungal infections that they were getting in upper respiratory. Okay.
But how about new hospitals being built now?
Well, they damn sure should be doing it. Okay, they should. Okay, and I'll tell you even a more sobering statistic. In 2007, the AARP finished an extensive study, about 10-year study, looking at nosocomial infection rates, and they found that in either the very young or the immune challenged patients and or on the aged, that the rates of infection they were getting, in the United States, they were getting over 200,000 infections per year. This is not what you went into the hospital for. You get an infection because you went to the hospital. Of those, almost 50% died. Nearly 50% of those people died. Now, they were aged, or they were very young, or they were immunocompromised. Okay, but
I've heard those statistics.
Those are real numbers, and that's the U.S.
I have a much more whimsical question.
I like whimsy.
Excellent. I noticed your Tyrell Corporation T-shirt, so I'm imagining that you get some inspiration from science fiction and maybe some of your professional choices. And I'm wondering, when you talked about programming surfaces to do different things, there's a lot of science fiction in which surfaces are really programmed to do different things because you have ones and zeros, it can change state. So I was wondering if you'd like to speculate wildly on that subject.
Well, I won't lie to you and say that the ring world and things like that, where you actually have living spacecraft, is something that's always intrigued me. The problem is that they are whimsical. Yeah. Okay. On the other hand, it really is driven, for me, it's really driven from a reality base. I know that we will never have long duration space flight unless and until we can figure out how to benignly control this plethora of microorganisms. It's like eventually we're going to have to figure out how to spin spacecraft and make artificial gravity. Things like that. I mean, there's some basic things we got to get figured out. Either they work or they don't. Okay, but long duration of space flight and especially long term living in space We've got to do it. So for me, it's not saying, wow, I want to build a living spacecraft. It's more like, I want to take this, I want to figure out how to take this living organism and let it live it in peace, basically, in the craft that it's in. And by the way, huh?
It's an engineering problem.
It's an engineering problem for me. And by the way, it's obvious to everybody in the room, I'm sure, is that certainly because I'm a space advocate, a space nut, I think about spacecraft as a crucible in which to develop these kinds of things. Obviously, hospitals, okay, cars, airplanes, any closed environmental system is going to benefit by a benign, non-toxic way to control microorganisms, or for that matter, self-clean. Yes, ma'am.
Hello. I know you want to put those coating on the spacecraft, so I just wonder, maybe I missed a little bit too. And do you have data like for those coating under extreme temperature, very hot, very cold, or the extreme radiation, or different compound,
Yes.
the atmosphere and the gravity, those kind of situations compared to other coatings?
Well, let me just limit it to extremes of temperature. Okay, we have to. You might imagine the military is very interested in if we're going to put coatings on tanks that allegedly are going to keep those tanks clear of neuroweapons. They've asked us, and we've had to do a bunch of studies to determine that, can I put this thing in Saudi Arabia and let it roll around the desert for a year, and will it still be active? Okay, so we've done a lot of, and the answer is yes. Okay, is there a point in the thermal? Is there a point at which the enzymes will actually no longer function? The answer to that is yes, but it is in the many hundreds of degrees of Fahrenheit. So we've done things like placed we did this with the Boeing company again. We placed these coatings on the top of rotor blades on Apache aircraft in the middle of the Arizona desert, and at 200 degrees Fahrenheit over many, many days, and they're fine. Okay. Cold doesn't do so much to enzymes. Colds, they don't work as fast. But really, really cold extremes just don't really have they don't denature due to cold on average. Okay. The other extremes you're talking about, radiation. We have irradiated some of the coatings. We've done some studies to show that standard ambient radiation isn't a problem. But if you get radiation hot extreme enough to actually cook the coating or change the polymer nature of the coating, you will also impact the enzyme. Okay. Basically, our rule of thumb is that if the coating survives whatever extreme it is you're going to address it to, the additives will survive. That's the rule of thumb. I'll give you an example. I'm running over my time.
People are still here, so keep going.
Okay. We recently had, in fact, I'm negotiating with this company right now. Unbeknownst to me, in comes a company that says, we have a problem. We build coatings for large freighters that transport natural oils across the ocean. They go to Singapore, they go to Malaysia, they get palm oil, they get date oil, they get some kind of exotic oil. We bring them over here to the United States, we offload them, and then we'll pick up something like jet fuel or sodium hydroxide or Skydrol or something, and we'll put it in those same 3,000 square foot tanks. And we've got to clean that oil. We can't have that vegetable oil in there when we're going to put jet fuel in there. Okay? How can you help us? Okay? So they ask us, can we place degrees in these tank coatings? The answer is yes. Now they ask us, will it survive the challenge of those? They have 7 different cargoes that they challenge these surfaces with. And believe it or not, that degrees works very well after it's challenged even at 50% sodium hydroxide. Because the coating survives, the additive survives. As long as that additive is nestled down in there and is protected by that coating, it survives. Are there going to be challenges that we won't survive? Of course. I asked that question, but yes, of course. Yes?
Are you doing any medical applications of coatings? For example, the coating nanoparticles that could presumably attack cancer cells at their feeding site by blocking hormonal receptors?
Yeah. There are people working on coatings for those.
But your company isn't involved with this?
Not yet.
Okay, because it's a promising field to coat carbon nanotubes, buckyballs, those kinds of things, and have them migrate towards feeding the cancer feeding sites.
It is. Our corporate mantra is, again, we want to build things
for large surfaces.
For large surfaces, but also we want to build them so that they are drop-in type additives. You don't have to hold your mouth just right. We want to just be able to stir them in the soup. That drives us.
The last two questions.
Yes, sir.
Okay, two things that kind of been on my mind. One is I've noticed that in hospitals and around and about, everybody has switched to waterless hand cleaning gels for disinfecting and don't have to wash after. You just take these gels and rub them in and that's it. And the other one is, in the recent years, they've gone to disinfecting the water in the San Francisco Water District. They went from chlorine back to chloramine, which they stopped during World War II because they needed the ammonia. Do you know anything about those two?
No. Sorry, I don't.
Your Bradley slide with the OPD talks gave me some Army flashbacks.
Ooh, I'm sorry for that, dude. I personally was in the Coast Guard for way too long.
Oh, you picked it right then.
I knew when I started to enjoy the smell of diesel, it was time to get out.
Yeah. One of the inherent problems with filtering chemical, it's in the Army, it's called NBC, Nuclear Biological Chemical Training. One of the historic problems is the duration which filtration works.
Right.
If you look at a gas mask under, it depends on how much pathogens are in the air at the particular environment, your gas mask filters may only last 30 minutes.
Right.
Your tank filter may only last 90 minutes.
Right.
When I saw your OPD tech, what flashed into my mind instantly was sort of like a biological chemical catalytic converter. Get rid of the HEPA filter joke, because you're not going to stop sarin gas with a HEPA filter.
That's right. That is correct.
Are you working on something like that, like the way we change, heavy metal catalytic converters, and we just send the airflow through this and catalyze the state? Is that something you're working on?
Yeah, we have it was kind of weird. We've reached back to really, really old technology. It turns out that it used to be that in the cotton gin era where you were milling lots of cotton, it was a problem for these people because there was so much aerosolized fiber in the air. I mean, the people were getting really sick working in these gins, and so they came up with air handling equipment that was based on a wall of water. If I don't have a board, but basically imagine if I could suspend a wall of water, say 3 inches thick, and it was a force field basically that I drove the conditioned air through, okay? Then it would clear those particles. It would take those cotton fibers out of the air, and they had a way to filter them out and what have you, but it did it. Well, when I was sitting in a group like this, a fellow came up to me and said, why wouldn't you put these enzymes and these peptides in water through which the air is actually forced? Because the reactions are instantaneous. OPD tox converts 15,000 molecules of sarin per second. And the same thing for the peptide. The peptides work instantly against a microbe. So we got together with this guy over in Houston. We built a mock-up, and the military's looking at it right now. Well, we'll see. I mean, you can't, right now it's things fill this room. It's gigantic. Okay. Are you not going to put it on an M1? Huh? All prototypes are unwieldy. Ooh, this one is.
We have one last question. Well, seeing all the coatings that you're talking about putting on the outside of the crafts, and it's not only the extreme temperature changes, like the vacuum space, the micrometeorites that can hit.
Yep.
The real challenge is that when only the elements combine, how long can these things last? Like a mission to Mars, for example. All these extremes, how can these coatings, how can they last against all the extremes combined over long periods of time? If they can't right now.
It's a great question. I don't know the answer to it. The only way to know the answer really to it is to put at least portions of them on a craft and launch it and analyze them when they get back. That's really the way you'll have to do it, okay? But if history is any guide, then I would suggest to you that if the coating survives, the additives will survive.
I see. Is there room for improvement on these coatings?
I sure hope so. My whole damn business plan is based on it. Yeah. No, yeah, of course. You know what's cool? No, actually, I didn't mean to be flippant. It's a great question, by the way. I told you that these things have worked basically out of the chute, and by that I mean we've basically just gotten the enzymes, gotten various polymer systems, mixed them together, tested, and it works. Okay? Now, we've reiterated that several times. We type peptides, and we're using antibodies right now. We're doing receptors, et cetera. But what's going to be really cool is when the genetic engineers can come in and design actual functional additives to address the coating environment. In other words, we will engineer the molecules so that they will actually be very, very well adapted to a coating. And coming from the different direction is the polymer engineers at Southern Mississippi, the people that I'm working with, can't wait to start to modify their polymers to host biological molecules. We've not done that. We haven't done any of that. So maximization is something that I'm looking very much forward to.
Steve, we have a special surface here that you can use as a testing service, I'm sure, maybe with some caffeine or something like that.
Thank you very much.
So
I appreciate it.
Everyone, please join me.
Let me tell you, I went to Arecibo just this over Christmas, and they had a cup like this, and there was one. They had pictures of it. You could buy it. It changed colors, which us paint guys are just okay. Changed colors. You could see the telescope, or it was black. And when you put coffee in it, it turned color. You could see the telescope. But I didn't read the sign very carefully, so I went up to the lady. I said, "I want the one that shows the telescope." She said, "They do. They all do." I go, "No, I want the one that shows the telescope." She goes, "You pour hot water in it." And it turned. I go, "I knew that."
Please join me in thanking Steve for his great talk.